Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss question bank on Module 3, Lasers and Fiber Optics. So, in today's presentation, I will discuss about Part A, which is on analytical questions. So, the first question is find the relative population of the two states in a ruby laser that produces a light beam of wavelength 6943 angstroms at 300 Kelvin. We need to find the relative population of two states in ruby laser. Okay. So they have given inputs as wavelength and temperatures. Okay. So the solution will be start with whatever given as input. So the input is wavelength. So lambda is given as 6943 angstroms, which is 6943 into 10 power minus 10 meters. And temperature also they have given it as 300 Kelvin. Okay. So to find the relative population between the two states N1 and N2. Okay. So the relative population between these two states N1 and N2 is equal to N2 by N1 is exponential of minus E2 minus E1 divided by kBT. Okay. So this is the formula. Okay. So E1, E2 are the energy levels and N1, N2 are the number of population. N1 is the population in E1 and N2 is the population in E2. Here Kb is Boltzmann constant. Kb is Boltzmann constant, which is 1.38 into 10 power minus 23 and joule per second. And then we have so now we have to calculate this exponential of minus of E2 minus E1 by kBT. So to calculate that, first we need to calculate E2 minus E1. Okay. So we know that if there are two energy levels, this is E1 and E2, and the number of population in E1 is N1 and population in E2 is N2 is E2. Okay, so the difference, the energy gap between these two states is Eg. Okay, Eg is nothing but delta E. Okay, so delta E, Eg is actually equal to delta E, which is equal to E2 minus E1. So if you can, we know the energy gap between the two states is equal to h nu, which is energy of a photon. So that we can write frequency in terms of c by lambda. So we have basically here Eg or E2 minus E1 is equal to h into c by lambda. Okay. By substituting the values of Planck's constant, that is 6.626 into 10 power minus 34, and c is velocity of light, which is 3 into 10 power 8 divided by lambda, they have given 6943 into 10 power minus 10. Okay. So we get the energy difference between these two states as 2.85 into 10 power minus 19 joules. Okay. Then we are going to substitute this E2 minus E1 in the formula. So this is the formula, N2 minus N1 is the formula. So N2 by N1 is equal to exponential of minus 2.85 into 10 power minus 19 divided by Kb is 1.38 into 10 power minus 23 into 300. So Kb value we know and temperature also we know. So this is 1.38 into 10 power minus 20 into 300. Okay. So by calculating the exponential of this, we'll get N2 by N1, the population ratio between these two states, as 8 into 10 power minus 31. Okay. So this is the population ratio between the two states E1 and E2 with populations N1 and N2. Okay. So we have calculated the relative population between these two states, E1, E2, that is found out to be 8 into 10 power minus 30. Okay. So let us go to the next problem. While calculating this exponential, we should be careful about using exponential properly in calculator. Otherwise, you will get a wrong answer, right? So exponential of minus E2 minus E1 by kBt. Okay, so the second problem is for a helium-neon laser at 1 meters and 2 meter distances from the laser, the output being spot diameters are 4 millimeters and 6 millimeters respectively. Calculate the divergence. Okay, so for helium-neon laser at distances of 1 meter and 2 meter, diameters are given. Okay, laser beam diameters are given as 4 millimeters and 6 millimeters. We need to calculate the divergence, so the spreading of the laser light. Okay, so the solution is that we need to find out the divergence. So we need to start with given whatever is given. So they have given distances, right? So the distances D1 is equal to 1 meter and D2 is equal to 2 meters. They also given diameters. So to avoid the confusion, distances we can take it as x1, x2, x1, x2. Diameters, D1 is 4 millimeters, so that is 4 into 10 power minus 3 meters, and D2 6 millimeters, so that is 6 into 10 power minus 3 meters. Okay, so the formula for divergence is R1 minus R2 by D1 minus D2, and here D1 must be greater than D2. D1, D2 are okay. So here whatever we are using is x1 minus x2. So x1, x2 are distances. So x1 must be greater than x2, and R1, R2 are radii. But here they have given us the diameter, so I am going to calculate the radius. So radius is d by 2, diameter by 2. Okay, so yeah, so I can calculate this radius as 4 by 2 is 2 into 10 power minus 3, and for this radius is 6 by 2 is 3 into 10 power minus 3 meters. Okay, substituting this in this formula, R1 minus R2, so 2 into, so here we have to use x1 must be greater than x2, so we are going to take x2, we are going to take this as R2, R1, and the distance as this, as x1. Okay, because of this condition, x1 must be greater than x2. Okay, so 3 into 10 power minus 3 minus 2 into 10 power minus 3 divided by 2 minus 1. Okay, so that is equal to 10 power minus 3, because 3 minus 2 is 1, 2 minus 2, 1. So 10 power minus 3 meters. The divergence is, divergence theta, for example, is 1 milliradian. Sorry, the divergence is in radians. So 10 power minus 3 radians are 1 milliradians. Okay, so this is the divergence formula. R1 minus R2 by x1 minus x2. Okay, so you always, this condition, you should always remember the condition, x1 must be greater than x2. Okay, so to avoid the confusion, we can write like this. The same formula we can write it as x2 minus R2 minus R1 divided by x2 minus x1. Okay, so then we do not need this condition anymore, because x2 is already greater than x1. That is how we defined x2. Okay, so R2 minus R1 by x2 minus x1. So that is the divergence formula, and x2 is greater than x1. Okay, better, x2 must be greater than x1. Okay, yeah, so we have calculated the divergence for helium neon laser at two different distances, and the divergence is turned out to be 1 milliradian. Okay. Okay, so let us go to the next problem, lasers. So the next problem is, a helium neon laser emits light at a wavelength of 632.8 nanometers and has an output power of 2.3 milliwatts. how many photons are emitted in each minute by this laser when operating. Okay. So we need to find out how many number of photons are emitted in this laser that is giving us output around 632.8 nanometers. Okay. So yeah, so we need to find out the number of photons emitted per minute. Okay. So solution start with always given, whatever is given. Wavelength lambda is 632.8 nanometers. So that is 632.8 into 10 power minus 9 meters. And output power is given. Output power is given as output power PO we can define as 2.3 milliwatts. So that is 2.3 into 10 power minus 3 joules per second. So we can we want it in per minute. So that is per minute 2.3 into 10 power minus 3 into 60 per joules per minute. Okay. Now, so we know the output power, and this is what they have given, right? Yeah. So now we need to calculate the number of photons emitted per minute. Okay. So to calculate the number of photons emitted per minute, first we need to know the number of photons emitted. Number of photons emitted is equal to output power, total output power of light divided by energy of each photon, energy of a photon. Because light is made up of photons, so this how much output we are getting, and then what is the energy of each photon, then we will get the total number of photons emitted in that light with some output power 2.3 milliwatts. Okay, so this is what we need to do. So this is the number of photons emitted. So we know output power emitted is 2.3 milliwatts per minute. Also we have done. Now we need to calculate the energy of photon. Energy of photon is h nu, right? So that is hc by lambda. Okay. So here they have given lambda. So h is 6.626 into 10 power minus 34 into 3 into 10 power 8 divided by lambda is 632.8 into 10 power minus 9. Okay. So by calculating the energy of each photon, then whatever value we get, we are going to take this and we are going to substitute here. Okay. So this E must be substituted here. So then the total number of photons emitted, photons per minute, is equal to 2.3 into 10 power minus 3 into 60 divided by the energy is equal to hc by lambda, whatever we get. Okay. So by substituting all this, whatever value you get, you substitute here. So the answer which we get is equal to 4.39 into 10 power 17 photons per minute. Okay. This is what we get as answer. So 4.39 into 10 power 17 photons are emitted per minute in this helium neon laser light, which has wavelength around 632.8 nanometers, and it has output power around 2.3 milliwatts. Okay. To simplify this solution, first what we need to do is that we need to calculate the energy of photon. The energy photon is h nu. So here they have given lambda as input. So we are going to write frequency as c by lambda. So basically we will have hc by lambda. Once we calculate the energy of each photon, so to find out the total number of photons emitted, we are going to find out the output power divided by the energy of each photon. Output power they were already given 2.3 into 10 power minus 3 because milliwatts, and per minute it is 60. And now energy of each photon we calculate. So total output power of light divided by the energy of each photon will give us the total number of photons emitted per minute in this helium neon laser light having wavelength 632.8 nanometer. So here we found that the number of photons emitted is around 4.39 into 10 power 17 photons per minute. Okay, so that is the solution of this problem. So the next problem is solve the value of the wavelength of emitted radiation from a semiconductor diode laser which has a band gap of 1.44 electron volts. We need to find out the wavelength of the radiation of this diode laser, semiconductor diode laser, which has energy gap is around 1.44 electron volts. Okay, solution. So whatever they have given is energy gap Eg, which is 1.44 electron volts. We can convert into joules. 1.44 into 1.6 into 10 power minus 19, and then we need to calculate the wavelength. So we know the energy gap Eg is nothing but the energy of a photon, because there are two energy levels, E1 and E2. When the atom decays from E2 to E1, the difference is emitted as a photon of energy h nu. So this is Eg, which is equal to delta E, which is equal to h nu. So hc by lambda. So from this formula we need to calculate lambda. So lambda is equal to hc by Eg. So yeah, so lambda is equal to hc by Eg. So that is a formula. H value is 6.626 into 10 power minus 34, and velocity of light is 3 into 10 power 8, divided by Eg is 1.44 into 1.6 into 10 power minus 19. So whatever what the value of lambda is 8633 into 10 power minus 10 meters, or 8633 angstroms. So this is what we get as answer. Okay. So the wavelength of the radiation that is emitted by this semiconductor diode laser is around 8633 angstroms. Okay. So using this formula of energy gap, Eg is equal to h nu or hc by lambda, we have calculated lambda. Eg is equal to hc by lambda. From this we can write it as lambda is equal to hc by Eg. So substitute the value of Planck's constant, velocity of light, and energy gap. We can calculate the wavelength of this light, which found out here as 8633 angstrom. Okay, so let us go to the next problem on lasers. So that will be the last one on lasers. A semiconductor diode laser has a wavelength of 1.55 micrometers. Estimates its energy band gap in electron volts. Okay. So they have given the wavelength here. Now we need to calculate the band gap. Okay. So using the same formula which we have used in the earlier. So given is energy. Yeah. So given is wavelength. Lambda is 1.55 micrometers. 1 micrometer is 10 power minus 6 meters. So 1.55 into 10 power minus 6 meters. So we know that Eg is equal to delta E is equal to h nu, because of these energy levels E1 and E2. When atom in from E2 decays to E1, the difference is emitted as h nu, which is equal to delta E, which is equal to E2 minus E1. So h nu frequency I am writing in terms of wavelength, so hc by lambda. What I need to calculate is energy gap. So this is the formula. Eg is equal to hc by lambda. So h is 6.626 into 10 power minus 34, and velocity of light is 3 into 10 power 8 divided by lambda, 1.55 into 10 power minus 6 meters. So the energy gap Eg is found out to be 0. Okay, so we want this, we will get in joules, but we want in electron volts, so divide by 1.6 into 10 power minus 19. So we will get 0.8 electron volts as energy gap. Okay. Yeah, so that is the solution. The energy gap of the semiconductor diode laser is found to be around 0.8 electron volts. Okay, let us go to the next problem. Okay, so these are the 5 problems on lasers. Okay, so now we will look at the next 5 problems on fiber optics. Okay, so the next 5 problems on fiber optics. Okay, so the first problem on fiber optics, our 6th problem in module 3 is a step index fiber has a numerical aperture of 0.16 and core refractive index of 1.45. Estimate the acceptance angle of the fiber and refractive index of the cladding. Okay, so solution. We need to calculate the acceptance angle and refractive index of the cladding. Okay, so whatever they have given is numerical aperture, which is 0.16, and N1 is the core refractive index, which is 1.45. We need to calculate the acceptance angle. So acceptance angle theta A is sine inverse square root n1 square minus n2 square divided by n0. But in general, we take n0 as 1 because we take n0 media is the media where we launch the light as air. So the refractive index of air is 1. Okay. So now substituting the n1. So this is basically sine inverse of numerical aperture, because numerical aperture formula is what? Numerical aperture is defined as square root n1 square minus n2 square by n0. So all we have here is numerical aperture. Okay. So sine inverse of numerical aperture they have already mentioned as 0.16. So this is what we get, 9.206 degrees. It's the acceptance angle. So next we need to calculate the cladding refractive index using the formula of numerical aperture. We generally take n0 as 1. So numerical aperture is basically square root n1 square minus n2 square. Squaring it out, we'll get numerical aperture square is equal to n1 square minus n2 square. We need n2. Okay, so we want n2. So that will be square root n1 square minus numerical aperture whole square. So substituting the core refractive index, which is 1.45 square minus 0.16 square. So the refractive index of cladding is found to be 1.44. Okay. Yeah. So okay. So we found out the refractive index of cladding as well as the acceptance angle of this strip index fiber. Refractive index of cladding is 1.44 and the acceptance angle is around 9.2 degrees. Okay. Using the formula of numerical aperture as square root n1 square minus n2 square by n0, but n0 is 1, so square root n1 square minus n2 square. So acceptance angle is basically sine inverse of numerical aperture. So numerical aperture they are given, so by substituting the numerical aperture in the acceptance angle, sine inverse of 0.16 is 9.2 degrees. Okay. So this is the solution of this problem. So the next problem is seventh problem. Seventh problem is the refractive indices of core and cladding materials of a strip index fiber are 1.48 and 1.45 respectively. Simulate numerical aperture and acceptance angle. Okay. So they are asking us to calculate numerical aperture and acceptance angle, and whatever they have given is a refractive index of core N1 1.48 and refractive index of cladding N2 which is 1.45. Okay, so we know the numerical aperture. Numerical aperture formula is defined as square root n1 square minus n2 square by n0. N0 they have not mentioned. The media they have where we launch the light into the fiber, they have not mentioned. So n0 is the refractive index of the media where we launch the light into the fiber. Okay, so n0 we take it as 1. Okay, so square root n1 square is 1.48 square minus 1.45 square. Okay, so the numerical aperture is found out to be 0.2965. Okay, so then we need to calculate the acceptance angle. Acceptance angle is nothing but sine inverse of numerical aperture. Okay, so sine inverse of 0.2965, which is 17 degrees 15 minutes. Okay, 1 degree is 60 minutes, so you can convert that into, so whatever you have 0.296 like that. If you get 17 point something degree, so that whatever points you are getting, that you can convert into minutes using this formula 1 degree 60 minutes. Okay, so we got numerical aperture as 0.2965 and acceptance angle as 17 degrees 15 minutes. Okay, so these are the two formulas. Numerical aperture is square root n1 square minus n2 square by n0, but n0 is 1, and theta acceptance angle is sine inverse of numerical aperture. Okay, okay. So let us go to the next problem. An optical fiber has a numerical aperture of 0.02 and a cladding refractive index of 1.59. Solve the value of acceptance angle for the fiber in water which has a refractive index of 1.3. Okay. So they are asking us to calculate the acceptance angle in water. So basically we are launching the light into the fiber in water, and they have mentioned the refractive index of the water 1.3. Okay. So solution is okay. So they have given input as refractive numerical aperture. They have given it as 0.02, and cladding refractive index is N2, which is 1.59. They are asking us to calculate the acceptance angle. So acceptance angle theta A is sine inverse square root n1 square minus n2 square by n0. So they are saying that without water the numerical aperture is 0.02. Now okay, so sine inverse, so numerical aperture, so we are defining this as Na by n0. So they have mentioned what is numerical aperture, that is 0.02 divided by water is a medium where we are launching the light, so that is 1.33. So sine inverse 0.22 divided by 1.33, so that is the acceptance angle, which is found out to be 8.65 degrees. Okay, so the acceptance angle is 8.65 degrees. Okay, so let us go to the next problem. Calculate the fractional index change for a given optical fiber if the refractive indices of the core and cladding are 1.563 and 1.498 respectively. Okay, so we need to calculate the fractional index change. So they have given us N1, which is 1.563, and N2, which is 1.498. And fractional refractive index change, fractional index change, refractive index change, delta is defined as N1 minus N2 by N1. Okay. So just substitute the values of N1 and N2, that's all. 1.563 is 1.498 divided by 1.563, which is equal to 0.04. Okay. So that is a fractional 0.0416 or whatever. So that is a fractional refractive index change. Okay, so this is the answer for this. Next problem. When the mean optical power launched into an 8 km length of fiber is 120 micrometers, the mean optical power at the fiber output is 3 micrometers. Find the overall signal attenuation and signal attenuation per kilometer. So we need to calculate the signal attenuation and per kilometer, attenuation per kilometer. So they have given us the input power, 8 kilometers the length, input power is 120 micrometers and output power is 3 micrometers. Okay, so yeah, so they have given input power Pi as 120 micrometers, P output power is microwatts, and P output power is 3 microwatts. And length L also they have given, length L is 8 kilometers. So the signal attenuation alpha is defined as 10 by L, alpha in units of per kilometers, log to the base 10 of Pi by Pu. Okay. So we want the first overall attenuation. So overall attenution is L, alpha into L. This is decibels per kilometer. Decibels per, we have not yet calculated the decibels per kilometer. So alpha L is defined as 10 log 10 into Pi by Pu. So substituting all the values, 10 log 10 of Pi, which is 120 into 10 power minus 6 divided by 3 into 10 power minus 6. What we will get is 16 decibels as the answer. This is the signal attenuation. Signal attenuation per kilometer. Okay, so that is 16 decibels per kilometer is by L. So 16 decibels by L is 8 kilometers. So that is 2 decibels per kilometers. We have 2 decibels as the attenuation. Okay. So in this problem we have calculated the attenuation, overall attenution. That means over the full length of the fiber, what is the attenuation? So that is why we have multiplied alpha with L. So the actual formula is this: 10 by L into log 10 of Pi by PO, input power divided by output power. But we want, this is decibels per kilometer. So per kilometer, this is the attenuation. But they asked us overall attenuation, right? So to calculate the overall attenuation, we have taken L to this side. So that alpha into L is the overall attenuation. So that is 10 into log 10 of Pi by PO. And then once we got the overall attenuation, then we calculated also per kilometer. So overall attenuation divided by length of the fiber is 8 kilometers. So finally we got 16 by 8 as 2 decibels per kilometer is the attenuation of this signal. Okay. Yeah. So we have solved 10 problems. 5 problems on lasers and 5 problems on optical fibers. Okay. So these are the 10 numerical problems on module 3, lasers and fiber optics. So these are some of the textbooks I have used and reference books one can look at. And to summarize, I have solved the numerical problems on module 3. So this is part A of question bank on module 3, lasers and fiber optics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.